IMF essays. All right. I wanted to put this in. As you've been watching all these videos, I had made them at a previous time, and I went over all the basic information for the different intermolecular forces. But I wanted to spend a little time going over essays that are in this chapter because this is one that AP loves to pick essays out of. In fact, really, chapters 7, 8, 9, and 10 in our book, which means everything from electron configuration, then to bonding, polarity, and then into this chapter, intermolecular forces. All of that, much of it can combine into just one question. Maybe not the electron configuration so much. I'm having a problem with my computer here. I'm not even using it right now, but I'll just have to cut it off. Okay. But anyway, so what I did was I made this list, and I'll probably talk about this in class as well. For sure, I'll mention it. But it talks about it gives you sample essay questions that you can see on AP, how they handle this chapter and how you should answer them. So what I want to do is all right. Let me just check. Maybe number 2 is a good one to start off with. Oh, no, actually, no, not that. Let me go over to the different properties. Yeah, I want to focus on intermolecular forces. So the first thing you should be aware of when you see a question that involves intermolecular forces, what are the intermolecular interparticle forces? IMF or IPF? We'll call it interparticle forces. You don't really have to. You can just say IMF usually there. But by the way, when you're writing an essay, if they ask you a question about intermolecular forces, you can say that, you can put a little key on your paper. Intermolecular forces equals IMF, okay? The strongest type of force we talk about is network covalent. That means you actually have covalent bond to bond to bond. The best examples I mention that all the time is diamond. In a diamond, you have a carbon to another carbon to another carbon, another carbon, another carbon. And this actually goes on in a network, and you get a diamond shape out of it. And all of these are tetrahedral. They're all tetrahedral geometries as they move along in there as well. Sorry, I'm making sure this is set up right. You know, I could go on and on and on. You could actually make a diamond like that as well, playing around with it. So network covalent, a diamond, sorry, or anything, silicon, diamond, carbon in the diamond, allotrope they call it. Or how about really any metalloid, any pure metalloid like germanium or arsenic. So any metalloid, carbon, diamond, or any metalloid, silicon's a metalloid, germanium, arsenic, but and almost pretty much any compound with silicon, like SiO2. Sometimes we'll put SiXOY, meaning you put any number there, and it might have some negative charge, negative N, we'll say. You can plug in any of those. They're called silicates. But any of those, silicon, any silicates, they all have network covalent. Okay, like sand, a grain of sand. And I'll mention that. So network covalent is number 1. Number 2 on the list is going to be metallic bonds. Number 3 is ionic bond or ionic forces. Number 4, 5, and 6. Now these become the molecular forces. Or if you want to call covalent. So if you can rule out in an essay, this chemical, this is not this, not number 1, number 2, number 3, but it's got to be one of these, you should draw the Lewis dot diagram. I know I mentioned that in there. The strongest of these molecular forces would be hydrogen bond. And that's another thing you can do. You can make a little key, and the first time you mention it in your essay, you can write hydrogen bond equals H bond. Okay? Or, you have dipole-dipole forces. You can put dipole-dipole, DD. or you can put LDF, London Dispersion Forces. So when you're writing your essay, the first time you write London Dispersion Forces, you can write LDF like next to it, or equals that, or whatever, like I did. And then from then on your whole AP exam or on your whole essay, you can just say DD, H bond, whatever. You don't have to go and rewrite the whole word out again. They'll let you do that. Now, if you don't make a little key and you just write those things, I'm going to take off some when I'm doing it. But now on the real AP, you might get somebody, get 2 people grade every question you do on the AP. So somebody might be lenient, but then they might say, wait a minute, they just wrote DD. What in the world? That could be, what does that mean? So anyway, so first you ought to have this in mind when you're doing these essays. Another thing you need to have in your mind are all the geometries of the shapes, all of those, with lone pair, without lone pair, and how to draw all the Lewis dot diagrams. Okay, so let's start off, and let me just show you an essay question. I'll skip over. I was starting off with the first page. The first page of the essays that I'm giving you, they really apply more with chapter 8 and 9. But now number 5 works out good. Okay, so here's the first one. Which has a higher normal boiling point, BF3 or BI3? Okay. All right, so BF3 or BI3? Oh, and I need to say one more thing. Boiling point. Okay, in fact, let me write a little statement here. Okay. As the intermolecular force strength increase, the blank increases. Now, what can I fill into that blank? As IMFs go up, what else goes up? The boiling point. So if particles are, well, okay, let's just take, we're going to talk about BF3 and BI3. I will tell you to draw the Lewis dot for those, but in fact, let me do that right now. I'll write BF3. So boron, you see it has 3 valence electrons. It's there as well. And then this one has fluorine on each side, and there are halogens all around them. Look how easy that is. So BFFF and BIII. And then, now, since they didn't ask you, if they ask you to draw the Lewis dot diagrams, you better make sure, I shouldn't even say that, you should always put in your lone pair. You better just get in the habit of always doing that. Now, the only thing is, if they don't ask you to draw a Lewis dot diagram and you draw them, and you leave off these lone pair, you might be okay. But if there was ever a lone pair in the middle and you left it off, you wouldn't be, because that wouldn't be a good way to explain it. So they would look like that, okay? Now, so remember, if one molecule of BF3 sticks to another molecule of BF3 and another molecule, those are called intermolecular forces. As those forces increase, the stronger they are, that means the boiling point increases. So, for example, if BF3 were to have ionic bond forces and BI3 had London forces, then you would say, oh, BF3 has this, ionic forces are stronger than LDF because stronger forces. But that's not the answer here. But that's how you want to look at it. You want to first look at the molecules and say, where do they fit into this little hierarchy? And it turns out BF3, okay, it's not network covalent. Now, I picked that question. Boron actually is a metalloid. But now, as a pure metalloid, pure boron would have network covalent in it. But BF3 does not. With the halogens, it does not. You can even have something called, I said silicates. There are even borates. B-O, like B-I-X-O-Y. And borates would have network covalent. How crazy that is. But not with the halogens. So you may not even know that little detail there, but now you've heard it. So this one is not network covalent. Okay, it is not metallic. No, that's not a metal bond. No, they're not ionic. Metal, non-metal for ionic. Metals need to be all metal or an alloy. Okay. Okay, so it means it's going to be one of these molecular. We draw the Lewis dot. It's not H bond. For H bond, you remember you have to have an H bonded to either F, O, or N. The Fonkel-Bridge, the first three letters. An H directly bonded to an F, O, or N. And then also the F or N is bonded to has to have some lone pair on it. And that will usually always be the case. But there can be some weird cases where that might not always work out. And then dipole forces, that would mean if they're polar, and that's if they're nonpolar. Remember that. You should know this little hierarchy by now. So these are both going to be nonpolar. Because you see, even though that's a polar bond, trigonal planar, they're in the trigonal planar geometry, and they're all 120 degrees apart, so the dipoles will all cancel. The BF will all cancel in the trigonal planar geometry. By the way, that's the way you would answer that question on another page. Is this molecule polar or nonpolar? It is nonpolar because BF3, you draw the Lewis dot diagram, has trigonal planar geometry, and all the boron to fluorine bonds, dipoles, the dipoles meaning the negative is that way, the negative is that way, for that one and that way. All three of them cancel out because they're 120 degrees apart in a trigonal plane geometry. That's the way you would say it. Therefore, it's nonpolar. Nonpolar. Since it is nonpolar, that means that the primary intermolecular force will be London dispersion forces. They have LDFs. They both have LDFs. So, now, I'm kind of jumping back and forth and answering the question, but I need to get back up here. This is an important statement. As intermolecular force strength increases, the boiling point increases. Also, the melting point would increase, okay? Also, you could say something like, what are some other things? Like the hardness of the material would be increased. We talked about surface tension. We mentioned it before. If you heard that word, surface tension would increase. Anything that would cause the molecules to be closer together. So, boiling point, melting point, hardness, surface tension. Try to think of what other things they could throw at you. They're all in the note packet. Let me see if I have anything down here. I don't have any. I can't remember many other ones right here. Oh, viscosity for a liquid. Viscosity. I told you viscosity is kind of like the thickness of a liquid, meaning that the molecules just get really sticky together, like that, really viscous, sticky and thick. So having stronger intermolecular forces means, yeah, it's going to be even higher viscosity. Okay. So what else am I looking at? I can't think of anything else right there. But now there are three. So these all increase, but watch this important one. As intermolecular force strengths increase, the blank decrease. The number one is vapor pressure. And I mentioned that on a video and talk about that, why that is true. Went through the long video about that. Less vapor above it. So having weak intermolecular forces means you have a high vapor pressure, or having strong intermolecular forces means you have a low vapor pressure. So, you could say high IMF means high boiling point, high melting point, higher hardness, higher surface tension, higher viscosity. But it would mean high intermolecular forces strong means low vapor pressure. It also means low evaporation rate. Okay, evaporation rate will be low. If you have weak forces, you evaporate really quick. Okay, but strong forces, they evaporate slowly. And then, heat of vaporization. Now that's one for sure in AP. In fact, I'm gonna make another video. I hadn't done it yet, but there's gonna be a video on this with calculation. But the heat of vaporization, if you have strong forces, it's going to be a lower heat of vaporization. But now, what about heat of fusion? Okay, heat of vaporization is the heat required or involved when a substance changes from a liquid to a gas. So it vaporizes. If you're going from a liquid to a gas, you got to add heat to something to make it go from a liquid to a gas. Okay? And so the heat of vaporization, as you have stronger intermolecular forces, then you have a lower, it talks about that, a lower heat of vaporization. I'm trying to think about that for a minute. Does that make sense? Wait a minute. Lower vapor pressure, lower evaporation rate. Yeah. Yes, because weak forces will have a, if they're very weak, strong will have a low and weak will have a high. No, you know what? That is wrong. Vela's putting a wrong thing on his essay video here. If you have strong intermolecular forces, then your heat of vaporization is going to also be higher. I'll let you know in our class too if I made a, yeah, that's not going to be the vaporization. The heat required to change a liquid into a gas, to break all the intermolecular forces, if they're strong, it's going to also be strong. Yeah, I'm sorry about that. But vapor pressure and evaporation rate, they're going to be low. Okay, but those two will be low, but not the heat of vaporization. Okay, all right. So it's important to know the hierarchy. It's important to know that these are the properties they deal with a lot. Okay, and almost all of them increase except for these two. The vapor pressure, strong forces meaning low vapor pressure and low evaporation. That's all it would be. Okay. So, let me see here. Let me just check this question. So the question was, I was trying to do number 3 here, and I kind of abandoned and came back. No, I'm sorry. Number 5. Which has a higher normal boiling point, BF3 or BI3? So you would draw them. They both have London dispersion. Now, remember, once you know the hierarchy, then you got to remember, what if if one was metallic, one was ionic, and one was London, then you say, oh, metallic stronger than London, and so forth. It'd be easy to do because that's stronger than the other. But since they both are London forces, now you got to remember the molecule that has a larger volume is more polarizable. Therefore, it will have a stronger temporary dipole. Okay, stronger intermolecular forces. So between these two things, we can look at the molar mass and say BF3 has a molar mass of, and I didn't even write it on the paper there, but let's see. It's going to be 10.81 plus 19. It's 67.81. And BI3 is going to be 10.81 plus very big, 126. Could be like 388. So now, you can't just say the molar mass is greater. That's not right. Because what really makes polarization occur is the volume, not just the mass. Because something could have a big mass and be very small and dense. But anyway, it doesn't really much matter because, look at this. BF3 is so small compared to BI3. That's very obvious, 388, 67. So boron, iodine are very, very large molecules. Atoms. Boron's the same, but the fluorines are very little small. I could even do that kind of way if I wanted to kind of exaggerate it. And remember, you could also get into the fact that fluorine's valence is N equals 2, but iodine's at N equals 5. Right? 1, 2, 3, 4. Yeah, at 5 farther out. So BI3 has a larger volume, therefore it is more polarizable. And being more polarizable means it has stronger London dispersion forces. Okay, so therefore, because BI3 has stronger London dispersion forces than BF3, it will have a higher boiling point. Is that what normal? Yeah, higher normal boiling point. I was making sure that I was reading the right question. Okay, so the things you want to mention in that question, the basic things are, number one, well, you want to draw the Lewis dot diagram for those, and you want to mention that both of them are nonpolar and have London dispersion forces. That's one thing you want to do. Lewis dot diagram number 1. Mention that they're both nonpolar, okay? Because and therefore they have London dispersion forces as their primary intermolecular force. Then you want to mention that because they both have London forces, the one with a greater volume is more polarizable, therefore has stronger London forces. Then you want to make that statement. Something to the effect of having stronger intermolecular forces means you'll have a higher boiling point. Okay, you gotta put that in there too. So it's almost like 4 or 5 statements that you want to make. All right, now that same question I continued on, and I went on number 6, and I don't really have to draw them again, but I just want to read what it says. Number 6 says, at room temperature, pretend it's a brand new question, or you'd never seen the one before it. Pretend you'd not seen the other question here. At room temperature, in comparing BF3 and BI3, boron trifluoride, boron triiodide, one of these substances is a solid and one is a gas at room temperature. One's a solid, one's a gas. Which is most likely a solid and which is a gas? Okay, so you go through everything that I just mentioned before, and you say that they both, everything will be the same. Everything will be the same, nonpolar London forces. And then BI3, BF3. Then you would say this. The stronger, or you have to say but stronger IMFs, stronger intermolecular forces will favor a more condensed state, or you can say phase. And what that means is, if your forces are stronger, you're going to stick together. That means if you want to be a solid, a liquid, or a gas, which one is more condensed? The condensed one will be a solid or a liquid, and a gas will be, obviously not condensed. So the stronger intermolecular force will favor a more condensed state or phase. So I said one's a solid and one is a gas. The weaker would favor the least condensed of the gas. So the weaker forces would be the gas. This one. And this will be the solid. From your predictions, write that. Now, if one were a solid, one were a liquid, then again, you say, well, that's the strongest intermolecular force solid. The next one will be a liquid, if they gave you another one there. If they gave you 3. But the weakest one will be the gas. The weakest of the groups that you had there. All right. So that's another thing to bring up. The states of matter, they've thrown that in there. Okay. All right. Oh, wow. What a misprint I had here. What a bad thing. I just read question number 7. I got to fix that thing right now. Which has a higher melting point or freezing point? Oh, and by the way, melting point and freezing point are the same thing. If it's mentioned, remember melting point and freezing point. Just remember they're the same thing. They both will. Stronger forces means a higher melting point. Stronger forces means a higher freezing point. Water freezes at 0 degrees Celsius. Ice will melt at 0 degrees Celsius. That's the melting point and the freezing point. So usually in what we do in AP Chem now, melting point is the term you usually hear most of the time. Where there's a unit that involves freezing point that is not focused at all anymore on the AP exam. Freezing point is there, and there's a really cool, great lab. I love it and everything. I miss teaching that, but oh well. Anyway, okay, so back to this. All right, number 7 says, which has a higher melting point or freezing point, silicon or fluorine? Now, it says answer silicon diamond. Silicon is not diamond. That's bad. I'm gonna fix those notes. But the answer is true. It is silicon has a higher melting point than fluorine. This is a very easy one to answer. So what you would do, silicon, fluorine. First of all, you'd say, all right, now they just said silicon or fluorine, I'll put F2, fluorine gas. So you'd say, okay, silicon has network covalent forces. Inner particle forces. They're all covalent bonds, silicon to silicon to silicon, in a sample of silicon. Now, silicone is SiO2, or has SiO in it. That's not the same. Silicon is pure element silicon. Fluorine would be nonpolar, have London dispersion forces. So, first of all, you identify what they have, and for that one I entered the Lewis dot. Now, you would want to say this: which is stronger? Network covalent forces are stronger than London dispersion forces. Okay, so first, network covalent fluorine has London forces. Network covalent, first state what they have, number one. State who is stronger. Network covalent is stronger than London forces. Then tie it into this. Having stronger intermolecular forces means you'll have a higher melting point or a higher freezing point. And so silicon therefore has a higher freezing point than fluorine. Now you can sometimes kind of fit a lot of those into one sentence if you wanted to, or you can just make it point. Just have all those points out would be a good way to do it. But if you want to say, well, silicon, I would first say these two. First, establish that that's network covalent and that's London forces, and then since network covalent forces are stronger of silicon are stronger than the London forces of fluorine, silicon will have a higher melting point than fluorine. Okay, and fluorine will have the lower. I guess it's good to put that in there anyway. That would get you credit though. But if you wanted to say, having stronger intermolecular forces means you'll have a higher melting point or boiling point. Okay. Now, here are some questions on number 8 and number 9. And I won't do all of these. You can actually read through these on here. But I'll start them off for you and show you that what has a higher melting point, CAS or LIF, okay? Or, I don't know which one I like to do better, CAS, LIF. I can do that one first. And then the next question says LIB or LIF. And I talk about this in the videos already. I already mentioned them to you. But you'd go through and you'd say, well, okay, these are two different questions. Calcium sulfide, lithium fluoride. Hopefully you'll see they're both ionic. They both have ionic forces. Now you want to go to Coulomb's law. And for Coulomb's law, the energy is actually called the lattice energy. You should know that. That's a terminology. Coulomb's law can be used to estimate the lattice energy. Lattice, think about the lattice is another word for crystal, like the structure, because just like you see a lattice, like they talk about a lattice has what would you call that? Like a little pattern. You see this like pattern of walls or fences or whatever, the lattice, whatever, different designs. Well, crystals have their own amazing geometrical design. So the energy to break something apart completely and turn it from solid, actually turn it to gaseous. If you did that, you'd break all ionic forces. It's called the lattice energy. The energy needed to completely take a solid and turn it to gaseous calcium ion and gaseous sulfide ion. That would be the lattice energy. And so you can estimate the lattice energy with Coulomb's law, Q1, Q2 over R squared. So, anyway, so this is the one where you've seen the video and I've talked about it. So you write down the charges. You say, well, they're both ionic, so positive 2, negative 2, positive 1, negative 1. And the product is the first thing you go for. 2 times 2 is, absolute value is 2. 1 times 1, negative 1, absolute value is 1. Since 2 is greater than 1, according to Coulomb's law, calcium sulfide will have a higher lattice energy than lithium fluoride. Therefore, calcium sulfide will have stronger intermolecular forces, if you want to say stronger ionic intermolecular forces than lithium fluoride. Having stronger ionic forces, having stronger intermolecular forces means you'll have a higher melting point. Yeah, they're both melting point or boiling point, if it was to say that. Okay, now, if you did like on the next question, positive 1, negative 1, positive 1, negative 1, they both have the same product. They're both 1 and 1. So now you go to the radius. And remember we told you, look at lithium and bromine. Lithium is the same size. So I'll try to draw a little circle. But which is larger, bromine or fluorine? If you can remember from chapter 7, bromine is larger. So I'm going to make it really exaggerated large and make fluorine really small. So now, who has a smaller and a larger radius? Center to center, there's the radius, and there's the radius. So what you would do, you'd say they both have ionic forces, and you would even say, since they have the same Q1, Q2 product, they both have ionic forces. Therefore, we'll use Coulomb's law to estimate the lattice energy. Okay, and because they both have the same product, Q means charge. The same charge product, magnitude, if you want to say that, absolute value. They're 1 and 1. Because they have the same magnitude for their product of Q1 times Q2, we'll look at the radius. And then you can draw a diagram like that and say bromine has a much larger radius than fluorine. If you wanted to add in, the valence shell of bromine is at level n equals 4, but at fluorine it's at n equals 2. If you wanted to draw that, that's even better. You can draw them and then put the circles in there. N equals 4, n equals 2. So, because of that, lithium fluoride has a smaller radius. Now, according to Coulomb's law, having a small radius, we divide this by a small number, that makes this larger. Small radius means you'll have a greater lattice energy. Then you say, so lithium fluoride would have the higher boiling point because it has a greater lattice energy. Having a greater lattice energy means you have a greater boiling point. Okay, so I talked about those, and I don't know, let me think about if there's anything else I wanted to say on the next pages. Some of them are polar. Now, obviously, if you drew them out, and if one molecule was polar and one was nonpolar, well then polar is stronger than nonpolar, and that would be the case. I've not seen any where they gave you one molecule was more polar than another. It could be done. I'll just show you, but there's a lot of other factors that can go in there with it. Oh, I know one thing I should mention. Maybe I do want to continue one. I might have to come back and continue. I might come back and continue one, or I might just wait and just tell you about it in class. But this is generally the pattern you need to follow for all of these. I guess in case I don't come back, I would mention that let's just say that you had water. If you drew water, H2O. If one of the things you're comparing is water, I mentioned this in some videos, but maybe I don't. Maybe I don't enough, or not clearly. Yeah, I think I at least hopefully say it. What is the primary intermolecular force in water would be H bond. But if you have H bond, you also have dipole-dipole in London. Okay? Now, if something else were only like fluorine, it only has London forces. It doesn't have anything else. If it had been HF, hydrofluoric acid, it would have dipole-dipole. It's polar, and it would have London forces. Still, this is stronger. What you care about is the strongest force. Now, I'll also throw in, they have asked questions that were exception to the rule sometimes. Sometimes something might have a higher boiling point even though its forces are weaker. Like, now this is not true for this molecule right here, but if it ever were true, if they ever said that, if they told you that this has a higher whatever melting point than this does, okay? If they ever told you that and you drew it out and you said, well, wait a minute, H bonds are stronger than dipole-dipole. But what you would say is, you would say, well, it's likely the London forces. But the London forces are so strong in this molecule that they overcome all the intermolecular force of the other. Now, that won't be true for water, but there are some times when London forces. I'll give you a good example is that has a higher liquid thickness? Oil, like motor oil, when you pour out oil, or water. You think about that. Well, water has stronger intermolecular forces, but oil has a more viscosity, resistance to flow, more thickness in the liquid. Why is that? It's because, why do they stick together? Because they have incredible London forces. So that, that affects that property is sort of like a little bit of an exception there. All right. Well, I'll see you guys later on, and I might put a second part on this.